This paper is about robust long-term object tracking via improved discriminative model prediction. My name is Seokeon Choi, studying at KAIST. This work was done while I was visiting researcher at CMU. First of all, we introduced the differences between short-term tracking and long-term tracking. In the short-term tracking setting, the target always exists, so we just estimate the bounding box of the target object. Different from this, long-term tracking requires an additional process because the target may not be present in this setting. So, the redetection mode is required for finding target after disappearing. And we must compute the bounding box with a confidence score. According to the confidence score, the system judges whether the target exists or not. In the training scheme, the video object detection datasets are commonly used because they contain the appearance changes of various objects. You can train a model using pairs of objects as the following picture. In the testing scheme, the bounding box of the target object is given only in the first frame of the video. So online learning is an important point to learn the appearance variations. We can say the object tracking task is a one-shot learning. We should keep track of object and also judge the existence of the target. Most importantly, a redetection module and measuring confidence is essential. Basically, long-term tracking follows this framework. As the first point, we have to judge the target existence and reliability based on the confidence score. As the second point, if it is determined that there is no target, redetection is necessary. As the third point, in most cases, pre-trained short-term trackers are used for tracking. As the final point, memory management is important. Likewise, we adopt the pre-trained short-term tracker which combines the bounding box regressor or PR-DiMP with the standard DiMP classifier. This tracker's name is Super-DiMP and the pre-trained model can be downloaded on the DiMP family's GitHub page. We omit detailed descriptions about short-term tracker. These are our contributions that enable long-term tracking to be robust. First is uncertainty reduction using random erasing. Second is random search with spatio-temporal constraints. Third is background augmentations for discriminative feature learning. We will explain our contributions one by one detail. This is our first contribution. We focused on the robustness, which is the consistent tracking ability, particularly against the artifact of background features. The robust model can consistently track the target, whatever occurs in the background, even whenever we remove some region of background. Let me see an example. The red bounding box is the ground truth and the yellow bounding box is the estimated result. In the left image, the prediction is not affected by background removal. On the other hand, the prediction is affected by background removal in the right images. If the prediction of our model changes when the small region of background is randomly deleted, we can say that the certainty is low. Thus, the right model is more uncertain. This is our concept and I will explain more technically. To make our model robust, we consider uncertainty as an argument and estimate the location of the target from the multiple images by randomly erasing the small rectangular areas. As illustrated in the above figure, most prediction results are not greatly affected. We correct the tracking flag of our model according to the agreement. This is our second contribution. As I mentioned earlier, in the long-term tracking, the target can disappear like the video on the left. So, the most of the long-term trackers use the redetection scheme. In general, they use a sliding window method for global search. However, this approach is too slow and not robust. To deal with the speed problem, we redetect targets stochastically. First, we created searching templates globally. Then we determine the number of searches adaptively. When the target size is large, we set the fewer number to search. When the target size is small, we set a more number to search, and we select searching template randomly. It is possible to search all parts within a few frames from a stochastic point of view. This method improves the redetection speed. And we want to say that the naive random search method is not robust. That means the redetection module proceeds as soon as the target disappears. At this time, a similar object can be estimated. Let me see an example. Once the target is missing, a new object is redetected. To prevent sudden detection of other similar objects, we penalize a confidence score through distance and time constraints. S is a confidence score and W basic indicates the basic redetection penalty. These two boxes are penalty terms. So, distance and time are more penalized than the confidence gets smaller. If the distance between new position and old position is large, the score is more penalized. However, this distance penalty is somewhat compensated by the time penalty as time passes by not finding the target. This metric solves the problem that the target is suddenly detected from a wrong distance. Therefore, it makes the proposed model more robust. The final contribution is about data augmentation. In the general setting, the short-term tracker is trained by using a target image. The most cases apply the data augmentation such as array flip, translation, rotation, and blur. We can see some examples in the left images. To learn more discriminative features, we augment various backgrounds. We can see the various background is synthesized with the person image. This approach enables training a more robust model against the background clutter. The more discriminative feature learning scheme is somewhat different depending on the situation. In the initial frame, the bounding box is given. It means the target image is completely confident. So we train the short-term tracker and store new generated images. However, the bounding box is not given in the remaining frames. So we train the short-term tracker with more generated images if the confidence score is high. And we never store the target features in the memory system because the tracker continues to be trained using the stored positive samples. These are our three contributions. We will explain evaluation metrics. In the long-term tracking, it is a bit different from that of short-term tracking. In the testing set, the bounding box and whether or not the target exists are provided as a ground truth. So we have to determine the existence of target based on the threshold for the confidence score. For instance, if the target higher than threshold, we judge the existence of the target and vice versa. And we can compute the precision recall plot for all thresholds. Finally, we can find the maximum F score at a certain threshold. This F score is main evaluation metric for long-term tracking. We compare our proposed method with the state-of-the-art methods in the VLT-LT benchmark. Our RLT-DiMP achieves comparable performance to the state-of-the-art long-term trackers in the VLT-LT benchmark. Notably, we achieve the highest score in the tracking recall metric, which means that our tracker is well modeled to be robust for long-term tracking through the three contributions. On the LTB50 dataset, a total of 50 sequences are annotated by 9 visual attributes. RLT-DiMP and Super-DiMP indicate our final version and baseline version respectively. We compare performance by adding each proposed module from the baseline. When applying uncertainty reduction, robust random search, background augmentation algorithms to baseline, the F scores are all improved. We note that our RLT-DiMP method outperforms the F score by 0.038 compared to the baseline tracker. In the visual attribute analysis, the proposed method surpasses the baseline tracker in all cases. especially in situations with visual characteristics of full occlusion, aspect ratio change, fast motion, and partial occlusion. Our method has an F-score performance of 0.05 or higher than the baseline. This is the demonstration videos of long-term tracking. Red box is ground truth. Green box indicates our previous VOTLT 2018 long-term tracker MMLT. And blue box expresses our new VOTLT 2020 long-term tracker RLT-DiMP. We can observe that our new method estimates the bounding box more accurately. And let's see another example. While the MMLT method often drifts to other objects, the proposed new tracker follows the target well with robustness. This is the last example. Clearly, the new RLT-DiMP tracker has high reliability in the target. Our method is implemented by PyTorch, and please let me know if you have any question. Thank you.